Our final module addresses the question of efficient Monte Carlo valuation. And you recall that we saw earlier that as n, the number of paths or the number of simulations increased, the standard error in our Monte Carlo estimate of an option price went with the square root of n, that we had to quadruple the sample size to cut our standard error in half. And so in this chapter, in this module, we're going to look at some ways of improving the estimate. For a given n, it turns out that there are various things you can do to make the estimate better than by simple Monte Carlo averaging. So same amount of work in the sense of you generate, still generate a sample size of n, but you get a better estimate. And of course, one might say, what does it mean to have a better estimate for a given size n? Intuitively, it means that for a given n, we develop an estimate that has a smaller standard error. And that's all that we mean. In other words, it's a procedure which for a given n produces a smaller standard error in the estimates than simple Monte Carlo. So we already know what Monte Carlo does, looks like 1 over square root of n. So any procedure that we can implement that does better than that would be efficient. It would be useful for us. So a very powerful method is a so-called control variate method. And the intuition is to say, if I'm estimating something, a random variable, and there's another random variable that I know how to estimate better, or I know what the error of the estimates are, I might be able to use the error of the second random variable to improve the estimate of the first. In other words, imagine that we knew that we had two random variables where the error of the first random variable was always half the error of the second. Well, if I could figure out the error of the second exactly, I would just cut it in half and adjust my earlier price, and the first price, by half of the error of the second. And I would have a better estimate. And what control variate does is to use this idea, but it doesn't demand that the errors have this simple functional relationship. All they require is that the errors are correlated. And so, so formally, here's the application. I mentioned earlier that we can use Monte Carlo to estimate Asian and geometric options. Now, if we denote by G and A the exact value of those options, G is known, A is not. I mentioned that there are exact formulas for geometric Asian options. There are not for arithmetic Asian options. So I can use a Monte Carlo estimate, say a Monte Carlo estimate with 10,000 paths. And I can use those same 10,000 paths for an estimate of the geometric and the arithmetic. Now, I know the exact geometric price. I don't know the exact arithmetic price. So what the idea of control variate would be is to say, instead of using AMC, the Monte Carlo estimate, let's change that estimate by adding the error in the geometric. In other words, if I have a let's imagine two situations. One where G minus GMC is equal to 25 cents. So I implement 10,000 paths, and I find that the Monte Carlo geometric Asian option is 25 cents less than the right price. And so what it's saying is, add 25 cents to your arithmetic Monte Carlo estimation, and that's going to be the estimator for the arithmetic. In a sense, I'm assuming here and this method can be refined. The book talks a little bit about it, but this is the simple idea of control variate. On the other hand, if you imagine that it was negative 25 cents, namely where Monte Carlo, the collection of paths I happened to generate, gave me a price that was 25 cents too big, control variate says, well, it's probably not unreasonable to think the arithmetic is also 25 cents too big. And therefore, I'm going to subtract 25 cents from my Monte Carlo price. So what it's doing is it's using the error in the geometric, which is known. I'm using the same paths for the geometric and the arithmetic Monte Carlo method, same paths. But if I know the error for one, I'm assuming I have the same error for the other. Now, when does this methodology improve the standard error of my estimate? What I'd like to be able to see is that the standard deviation, what I'd like to show is that the standard deviation of the A stars is smaller than the standard deviation of the AMCs. If this procedure can somehow produce a collection of estimates that have smaller variability, then this is improving my efficiency. Because for any collection of paths, I can easily generate the geometric and the Asian price, geometric and arithmetic Asian price. I know the exact geometric price, easy calculation. So this is the key. Can I show that?